Oh, yeah, sure.
Before we turn things loose for Joe, I have two things. One is an announcement that I was asked to ask about. This is from the people who run the dorms, and they said, ask if anyone was let into a meeting room, a classroom on the first floor of the dorm around 11 o'clock Sunday night. Okay? And that's all I would. That's all I repeat what I am told to do. Okay.
What are you supposed to do if someone says yes?
Huh?
If someone says yes.
Come and talk to me. Okay. That's the second part of it. Apparently, there was a list written on a blackboard on the pros and cons of suicide. I am just telling you.
Ooh.
I report. I wasn't supposed to say this to you. Okay. This frightened the person who saw it. The second thing is a little bit more public. Nobody is responsive yet. Okay. This last week at TASI, we have a Buffalo Shake principal. Okay. So, I'm holding in my hand a survey that we made up. I'm going to pass it around. I don't want to. I'm not going to look at it until next week. And then Oliver and I and Sherry will sit down and stare at it and try to figure out what to do next year. So I'm going to pass this around, and you can either give it to one of us, and you get around to filling it out before you leave town, or I'll put a folder out there by the copy. Okay. And our speaker today needs no introduction. Give me money.
Okay, now I get to be the one with the squeegee. So watch out if you're in the front row. So the subject of my talks is the black hole information problem, and should see how late I started so I can argue with the session chair. Okay. But the larger question that underlies this is, what is the theory of quantum gravity? And of course, for quantum gravity, string theory is a pretty good start. Let's draw some couple of string graphs here. It solves the problem of the non-normalizability of gravity. It does a lot of other good things. But the reason that we're not done, the reason that we weren't done, 30 years ago, well, the main reason is that it's just a perturbation theory. As in quantum field theory, this series doesn't converge, it doesn't define the theory, and we know that quantum systems usually have a lot of interesting and important phenomena that the perturbative series doesn't capture. In the standard model, we have quark confinement and chiral symmetry breaking and electroweak, baryon and lepton number violation, and none of them appear in the sum of Feynman graphs, but they're all there. So in the case of quantum field theory, this problem was also faced. It was originally understood as a diagrammatic theory, and it was really Wilson, I think, who sort of enunciated this problem in the 60s and solved it. He said that what this is an approximation to is basically the path integral, but moreover, the path integral as defined by the renormalization group. Now, the most direct, if we were trying to sort of learn from history, the most direct thing, therefore, to try in string theory would be something like string field theory. but so far, string field theory doesn't really seem to have, it has some elegant features, but it doesn't really seem to have given out much more than is put into it. It doesn't seem like it points the way to the solution to this problem. It seems like we need something more imaginative. And we found something more imaginative by way of dualities. So string theory, we now believe, is dual to quantum mechanical systems, the Banks, Fischler, Schenker, Susskind matrix theory, and a year later, ADS-CFT duality. And for example, in principle, these and quantum field theories and quantum mechanical systems are again things that we have an exact definition of, a la Wilson. And if this duality is correct, then in fact hidden within this quantum mechanics or quantum field theory are both the individual terms of this expansion, the things you learn how to calculate in string theory, and also the exact amplitudes to which these are the asymptotic series. Of course, these theories are strongly coupled, so only in sort of limits can one really see this structure emerge, but actually numerical work is progressing, and there's every reason to believe the full theory is in there. Now, there's lots of reasons we're not done, but the main reason is that these dualities construct string theory or quantum gravity only in very special spacetimes. Spacetimes in particular have very special boundary conditions. They don't include cosmological spacetimes. They don't include realistic compactifications. And even though we've had these now for 20 years, there seems as though we're missing one or more concepts to extend these lessons to a full theory. Now, to get to where we've gotten, thinking about black hole quantum mechanics has been a very useful thing. Thinking about the black hole entropy and what its statistical origin, and about the information problem really forced people to think about the relation between D branes and black branes, which was eventually crystallized by Maldacena as ADS-CFT duality. And you could ask the question, do we have more to learn from thinking about black hole quantum mechanics? Well, actually, the inside of a black hole is a lot like a cosmology. The geometry is not static. There's a singularity. So maybe it's a good thing to think about the inside of a black hole. What are the open questions? Well, so as I will review, these dualities imply that information is not lost. They imply that Hawking's original bold claim is wrong, but they don't explain what was wrong with his argument. And we still, after 40 years, don't know what was wrong with his argument. So there's kind of a challenge there. And people have continued to push on this problem after the dualities. And of course, the most recent thing is this AMPS argument, where a few years ago, basically by taking Hawking's original argument and kind of running it backwards, reverse engineering it, argued that if, in fact, information is not lost, then quantum gravity as an effective field theory, that was basically, a black hole, the information problem only deals with the black hole at times when it's large and its curvature is small, where you would think gravity would be valid as an effective field theory. Somehow, that assumption must break down in some way we still can't quantify, and the AMPS argument says that it breaks down in a rather serious way right at the black hole horizon. And so I'll talk about that and what the alternatives might be. I should mention entanglement. You've heard that word a lot. It's remarkable how entanglement and entanglement entropy have become central to many fields. With the Ryu-Takeyanagi conjecture, they are playing a central role now in understanding how space-time emerges from dual theories. As you heard this morning, in condensed matter physics, they're playing an essential role in understanding exotic phases of condensed matter systems, entanglement plays a key role in quantum information theory, where it is a resource. It's basically the currency, I guess, of quantum information. And entanglement also is key to the information paradox. So there's this incredible convergence of ideas. Just as an aside, I was here 5 years ago, the last formal TASI, which was a big component of which was applications of ADS-CFT, including condensed matter physics. And I cannot remember the word entanglement coming up even once. Tom is also shaking his head, which is, and Oliver, which is rather remarkable when you consider what you've heard during these 4 weeks. The words you heard a lot about were hydrodynamics. I think that was probably the most prominent thing, and quantum critical points. But somehow entanglement hadn't surfaced. Even though Ryutaki Nagi was then about 3 years old, it hadn't really risen to the surface. But now, actually, there's this tremendous sense of tremendous convergence, and one can't know where it will be, but it certainly reminds me of sort of the convergence of ideas that led to ADS-CFT duality itself. So what I'm going to do today is to start at the beginning, talk about the black hole geometry, derive Hawking radiation, start describing the information paradox, probably not finish, and then in lecture 2 I'll finish talking about the information paradox and start talking about what we learn about it from ADS-CFT. And I encourage you to ask lots of questions. Okay, so the black hole metric. So here's the Schwarzschild metric. In 4 dimensions, to pick a random number. And to get some conventions straight, R sub s is the Schwarzschild metric, 2gm, m is the black hole mass. And so I'm working in units where I'll keep the g's, but h bar, c, and I guess also Boltzmann's constant are 1. So for example, Newton's constant is equal to the Planck length squared, or to the Planck mass to the minus 2. So the first thing that I want to do is to work to see a little bit. So of course, Juan and Mark have scrawled black holes all over the blackboard, but I'm going to need more than the picture. I'm going to need some of the coordinate systems and all. And so I want to actually go through how one sees that the apparent singularity at r equals r sub s is actually just a coordinate singularity. So let's focus on the geometry near the Schwarzschild radius. Let's expand r equals r sub s plus delta and keep only the leading terms everywhere. And the metric goes to a linear piece, a piece that's 1 over linear piece, and then plus just the metric of a sphere. I probably won't keep writing the sphere piece for now because it's always going to be the same, but let me keep massaging. So this will always be implicit. Let's keep massaging. Oh, by the way, I've put, in case you haven't seen, the notes that I'm lecturing from, which are a work in progress, are on the TASI website, and I'll update them every day or 2. Okay, so this doesn't quite look familiar. To make it look a little bit more familiar, I'm going to redefine delta is rho squared over 4r sub s, and then this becomes minus rho squared over 4 r sub s squared dt squared plus d rho squared, and then I'll, again, leave off the series. Now, this might look almost familiar, but it will look even more familiar if instead of considering this geometry, we consider the corresponding Euclidean geometry, where we just analytically continue t goes to I t Euclidean, oops, I guess actually the minus IT Euclidean is not that it really matter. And then this becomes rho squared over 4r sub s squared d t sub e squared plus d sub rho squared, which is just the metric of 2 dimensions in polar coordinates if we define theta. I've already used theta, psi, I guess. That's an angle. So if we define psi to be t sub e over 2, that's r sub s, then this just becomes the metric of the plane in polar coordinates. And so this point, delta equals 0, which becomes rho equals 0, is in fact just a coordinate singularity of polar coordinates. The Euclidean case in a second, because it's interesting in its own right. But watch, let me let me first continue with the Euclidean case. So in the Euclidean case, then what we want to do is we would want to define x to be rho cosine of that angle, y to be rho sine of that angle, and so then the Euclidean metric just becomes dx squared plus dy squared near the horizon, plus the spherical part, plus the part's higher corrections as you move further out. So in the Minkowski space, we're going to define then x to be rho cosh t over 2r sub s, t to be rho sinh t over 2r sub s, and now ds squared is just d minus dt squared plus dx squared. So again, the apparent singularity at rho equals 0 is a coordinate singularity, and here are some nice coordinates which are completely smooth at the origin. Question, please.
So why are we demanding that the jumping not have the conical?
Well, I haven't really quite demanded that. You're jumping ahead. I haven't told you yet what the range of psi is. So far I'm just doing out. You're correct that it's a good question. I postponed it by not saying what the range of psi is. I just as a matter of change. But okay, good. So I suppose if psi had the wrong range, then the origin would still be a singularity. We'll come back to that. In the Lorentzian case, there is no analog. Because we have Sinches and Cauchys, t is not a periodic variable. So that's why I deferred that. There's no periodicity here, and so. But what there is in the Minkowski case that you don't see in the Euclidean case, and I guess I'll put that here because I don't mind covering it up later. Let's draw again this global coordinate t and this global coordinate x, and the region that these coordinates cover, you see, is when x is greater than the magnitude of t, which means they don't cover the entire, they only cover region 1 here. They only cover region 1 here, where x is greater than the magnitude of t, but the full metric then has these regions additional regions 1, 2, 3, and 4. It's also useful to go to light cone coordinates where u increases in this direction. Sorry that it's dark. That's a capital U. V increases in that direction. And so u is just t plus. Actually, I always forget which is which, so let me look at my notes. U is t minus x. Actually, while I'm at it, I'll write it in terms. This is minus rho e to the minus t over r sub s. And v is t plus x, which is rho e to the t over r sub s. Notice, by the way, that the relation between these global coordinates and the time that we began with, the time which goes over to ordinary time far away from the black hole, is exponential, something which is going to come up, of course, significantly later on. Okay, so again, staying with the Lorentzian case, so far I've just to make the expression simpler, focused on the region of the apparent singularity, but there is a corresponding coordinate transformation for the full geometry. I think maybe I'll do what Mariangelo did and say, I'm just going to stand here till you derive it. No? Okay. The s squared is, before I, yeah, sorry. So by the way, in terms of my light coordinates, this metric becomes minus du dv, and I'm going to write the full geometry. I'll try to put this, I'll try to at the very bottom of the board. And all of these equations are online. But now the fun part, I get to draw some pictures. So I think I'll put the pictures on this board over here. Yeah. So we're not going to have much use for the full expression. It's really going to be the near horizon geometry that controls the interesting physics. Okay, so let me draw then. I drew the. I guess it's already covered up the little UV. Something I can raise. Yes. So here is the u-axis. Here is the v-axis. They go on. Everything goes on to infinity in these directions, but here we have singularities, which you see the singularities are when little r is 0. Oops, there's a factor of r sub s here. I forgot. When uv and when little r is 0, and so uv is r sub s squared. Now, in order to fit the picture into a more compact space, one can simply do a reparameterization of u and v, just to basically to pull infinity into finite distance, and that's how it's usually drawn as a Penrose diagram. So this is u equals minus infinity. This is u equals 0. This is u equals infinity. This is v equals minus infinity. v equals 0 and v equals infinity. Okay, so actually that's probably not the picture that that Juan and Mark drew. They probably drew, this is Schwarzschild, but they drew Schwarzschild ADS. Which is the same in the horizon region, but different asymptotically. For today, I'll be focusing on black holes that are in flat space, and so I'll be thinking about this picture, and then in the next lecture I'll be thinking about this picture that I've just drawn. And the big difference, of course, is that here, remember, in Penrose diagrams, light rays move at 45 degrees. So in this picture, light rays leave the past horizon, this is the past horizon, and escape, or they come in from infinity and hit the future horizon. Here, something that leaves the past horizon hits the boundary and falls back into the black hole. So that's the big thing about ADS space, is that light-like trajectories can reach the boundary and come back again in finite time. Now, again, Juan and Mark were very focused on what I've drawn here, which is kind of the maximum vacuum solution to Einstein's equations. And what it is it's actually two black holes, this one and one over here, or here, connected by an Einstein-Rosen bridge. So the geometry kind of narrows and then gets big again as you move through. And I get confused by two-sided black holes. I think that there are conceptual issues that we just haven't understood yet. Maybe I'm wrong, but I think conceptually it's much easier to think about having a single, start with the simplest topology. Think about a single Minkowski space or a single ADS space and bringing it together enough matter to form a black hole and then watching what it does. So that's a one-sided geometry. In terms of these pictures, the infalling matter would be following some trajectory like that. Oops, I want to draw it time-like rather. So it would be following some trajectory like that. And only this part of the black hole geometry above the infalling matter would be relevant. The part below would be replaced by just the smooth space-time that exists, the empty space-time that exists, the empty one-sided space-time that exists before the black hole formed. And for most purposes, we don't care about the transients that occur right after the black hole forms. We study the black hole long after it's formed, and so one can kind of do a boost on these coordinates where this infalling body is pushed back almost to the this past horizon, and so our geometry is primarily regions 1 and 2. Good. And we're not so sure about 2. Okay. So now let me return to the Euclidean black hole and the question that was asked. And so, indeed, if you just at the level of changing variables, the Schwarzschild metric becomes the metric on the plane in terms of these coordinates. But now you see this coordinate. This is only well defined. It's only smooth, at least at the origin, if t has the right periodicity. That is, only if t sub 8 is periodic, with period 4 pi r sub s. If we consider, so let's consider again this geometry I've described here with that periodicity. Then what the geometry looks like is this: out at infinity, the time direction is periodic with the indicated periodicity, and as we move in, the time direction, because GTT is going to 0 when we get to r sub s, the geometry pinches off, and precisely if we consider Euclidean geometry with this periodicity, then the metric here near the tip is just this smooth metric, and the whole space is smooth. And now, what is this good for? Well, let's imagine that we now do the path integral for quantum fields, for some quantum field on this space. What is it describing? So, as you know, I think a path integral with a periodic Euclidean time is actually calculating a thermodynamic partition function. It's calculating, so if t is periodic t plus beta, this is like calculating the trace of e to the minus beta h, because h generates the translation in the h generates the, without the I, generates the Euclidean translation, and with the periodic identification produces the trace. So when we calculate the path integral on this space and various perturbations of adding in sources and so on, we're calculating a thermodynamic. We're calculating equilibrium thermal properties, and what this geometry is telling us is that the path integral on this space describes a black hole in equilibrium with thermal radiation of so beta is 1 over the temperature. So it's describing a black hole in equilibrium with quantum fields at temperature T sub h, which equal 1 over the periodicity. You can ask what if you took a different periodicity and put a conic singularity there, what would that path integral mean? And I'm not sure. It's a question that comes up now and then, but this is the claim. And if we're going to, so this leads us to the conclusion. Well, if it's true that a black hole can exist in equilibrium with a gas at finite temperature, of course, there's going to constantly be quanta falling into the black hole, and it must be therefore true that there are constantly quanta emerging from the black hole, and so the black hole must have a temperature. Sorry. Yes.
Presumably, this reasoning also works for ADS black holes.
Yes, it does. Yes. So let me think if I have anything to say there. So. So by how to define it, mean because of the scaling. So if we're talking about global ADS, then the field theory lives on a 3-sphere, and in effect, all temperatures are in units of the radius of the 3-sphere. I'll try to remember that question and come back to it when we actually talk about ADS black holes, because to be honest, I always have to remind myself how this works, because there is this infinite warp redshift factor. But let me in fact return to that. Another question?
Sorry, Joe.
Yes.
So this issue about the conical singularity, a sleek way to say that in your original solution you don't have any source.
Yeah, I guess it's not really a solution to Einstein's equation. It's right. I mean, maybe the simplest answer to say is if you put the conic singularity, it's not a solution to Einstein's equations. Yeah. Thank you. If you try to differentiate with respect to temperature, that's when you start thinking about this geometry, but I don't like to do that. Question, please. Well, so I'm saying, well, I mean, the assertion is that, well, let me just make the physical assertion, and then I'm not sure. If we put a black hole in a space filled with gas whose temperature is equal to the temperature of the black hole, those two things will exist in equilibrium. The amount falling into the black hole will be exactly balanced by the amount coming out. So I think. Oh, I'm sorry. Oh, sorry. Excuse me. Very good point. Very good point. There is a higher order. Oh, I'm sorry. Right. No, you're right. There is a higher order of. Right. The gas. Thank you. I spoke too quickly. The gas itself has energy. It back reacts. It changes the geometry. So in fact, this is some limit in which that effect has been made small. Thank you. I hadn't thought about that, but you're quite right. Yeah, maybe. I mean, right. We can start putting it in a box so that there's a limit to where. Yeah. Yeah. Good. Let me not pursue the logic of that too far, because the conclusion is right. That's all that matters. And as Shanta suggests, there is some order of limits in which the derivation is true too. In any case, what I want to do next is to actually study explicitly Hawking quantization and see the production of Hawking radiation, but I wanted to preview it in this way. I have to think about again. This gives you This gives you a certain limit of the problem, and in particular, if you're interested in correlation functions, Euclidean correlation functions in the presence of the black hole, this is a correct way to calculate them in some limit. But there, yeah. Good. So if I had a nice way to cut off the space, the back reaction wouldn't get too large, and I could cut off with ADS. But then I have to remember the answer to the question I already deferred about how we normalize the temperature in ADS. Yeah. Question? You mean here or anywhere? Oh, sorry. Pardon? In the world? Oh gosh. What a question. Aren't you using infinite warp factors and stuff in your talk? No, you're actually not using ADS, I guess. Yeah. What can I say? I don't know. This is yeah. So at this hand-waving level, we've. I'll ask you the same question during your talk. At this hand-waving level, we've concluded that the black hole has a temperature, and therefore, by thermodynamic relations, it has an entropy. ds is dt over m, and again we have that m. We have again that m is 2gm is r sub s. This is r sub s over 2g. And so we can integrate this and conclude that S is pi r sub s squared over g, which is the area of the horizon over 4g. And this fact is much more general than the the specific Schwarzschild black hole. It seems to be a property of all black hole horizons, even for charged and rotating black holes. Okay, so shortly, actually, or maybe it's now. Yeah, let me let me actually try to ask what this entropy might be, because there's in thermodynamics, statistical mechanics, entropy counts the number of available states of a system, and if I ask you what is entropy counting, you're going to start telling me about D1 branes and D5 branes or whatever your favorite brane construction is. But actually, it's worth remembering that long ago, Bekenstein, before even Hawking, inferred the existence of this entropy, and I'll review his argument. I'm not sure, there's a lot of strange things about it, but it's useful to kind of set the stage for some later discussion. So again, I'm drawing only the part of the black hole that I want, that is the part that forms in collapse, and I want to consider a space-like slice. So it's less than 45 degrees, so it's space-like. Metrically, it's very, very long inside the black hole. This is a conformal diagram, and so as you approach this point, you're actually going infinitely far. Now, suppose we sit on the outside, and suppose we start with a small black. Let's forget about radiation for now. Suppose we start with a small black hole, and we start feeding it quanta. And these quanta then end up on this slice. And let's suppose, for each quantum, there's kind of order 1 bit of information, which is sort of whether we throw it in or not, or maybe it has a spin, which way the spin points. And so the number of states, actually, the number of states available is of order E to the number of particles that we threw in. Bits or qubits, whatever. I'm just counting the log of the number of available states. I'm not being very precise here. In fact, I believe that Bekenstein's calculation, which I'm giving you, doesn't stand up to close scrutiny. So don't take it too seriously, but it's worth having seen it. Okay, and so the energy of each quantum, I'll call them quanta. The energy of each quantum, in order to fit inside the black hole, its wavelength can't be much longer than the size of the black hole. So its energy is of order 1 over r sub s. And so what we have is that the change in the mass of the black hole is of order 1 over r sub s times dn, the number of quanta that we've thrown in. And dm is d of 2g r sub s. And so we can integrate, and we can so inserting this, we can integrate, and we can conclude that the number is of order r sub s squared over g, which is again what we get from the Hawking temperature. So before Hawking, just by thinking about this thought experiment, he concluded that if I start throwing bits into a black hole, there's a sort of a limit to the information, the number of states, the information carrying capacity of the black hole, which indeed is just the statistical version of the Hawking entropy. I don't know if this argument has any validity at all. I think my colleague Don Maroff would say no. I mean, for one thing, well, two things. One is when the black hole starts evaporating, things get more complicated. For another thing, you can actually throw in more than 1 bit per quantum if you sort of throw them in slowly enough. And so I know that Bekenstein really tried to get the 4, tried to get the actual number in here. and thought he had some success. But this is a cartoon to remember. I don't know if it's actually going to play an ultimate role in our understanding of black hole entropy. Okay. But I'm going to draw pictures similar to this later on when I get to the information problem. So now let me do the calculation of Hawking of production of Hawking quanta for you. And I think it's squeegee time. Yes. Wait a second. This one does move up, right? Yes. Oh, okay. We have one more. Good. Okay. So actually, let me first go back to my pictures. So let me draw it bigger. So let's consider an observer who falls into a black hole, and another one who stays outside. And the infalling observer is sending, let's say, some regular signals like that. And they will only send a finite number of signals. Before they pass through the horizon. But if you're staying outside, clearly it's going to take an infinite amount of time for sort of the last pulse to reach you. So there's a very nonlinear relation between the proper time tau of the infalling observer and the time t that appears in the Schwarzschild metric, the time of the asymptotic observer. In fact, from the coordinate transformations, you can readily see that it's exponential, that d tau is e to the minus t over r sub s dt. So for fixed d tau, dt gets exponentially long. For fixed dt, d tau gets exponentially small. Now, this nonlinear relation between these time coordinates means that if we take a quantum field and we expand it in modes that are modes of given tau frequency or modes of given t frequency, there'll be a very nonlinear relation. In fact, there'll be a mixing of positive and negative frequencies. What one observer sees as purely positive, the other will see as mixed. And so in particular, the state that the infalling observer perceives as vacuum will be an excited state for the asymptotic observer. Also, something which plays an important role. So imagine that we're sitting, so when we're sitting on the outside, we're talking about modes that have a given frequency which is of order 1 over the Schwarzschild radius. For this black hole, there's only one scale, its size, the corresponding time is its light crossing time, the corresponding frequency is the inverse. So on the outside, everything we're talking about is at roughly the same scale. But so think of this as a delta t of order the Schwarzschild radius. The corresponding d tau is extremely short, becomes exponentially small. And so if we follow these modes back in time, the modes which are going to become the Hawking quanta have extraordinarily high frequencies when the infalling observer meets them. Okay. So, good. In fact, because this is fairly important. Okay, no, yeah. So John mentioned the adiabatic principle, and the adiabatic principle is going to play an important role for me. So let me actually here in the center talk about the adiabatic principle. So the adiabatic principle says that if we have some Hamiltonian and its parameters are changing in time, as long as the rate of change is slow compared to the mean spacing of levels, then you will stay in the ground state with very high probability. The probability of an excitation is exponentially small. So again, actually, I guess Eva, did this come up in her talk? So if the frequencies are changing at some rate, we form this dimensionless parameter, which is sort of the dimensionless rate of change of the Hamiltonian. And again, the probability of an excitation is exponentially small in this. Now, where I'm going to use this is in this geometry. And let me draw it in the center here. I'm going to imagine choosing some set of I guess maybe u plus v would be a good time coordinate, but it's some time coordinate which basically doesn't do anything too singular at the horizon. And if we think about a quantum field, and we think about sort of its Hamiltonian description in terms of this time, well, the Hamiltonian is changing because the geometry in these coordinates is changing. But again, the scale, it's changing slowly in a certain sense. It's changing slowly because the characteristic scale here is, again, 1 over the Schwarzschild radius. Whereas I just emphasized the fact that the modes that we're talking about in the neighborhood of the horizon have frequencies much, much higher than the other characteristic scales, because by this exponential blue shifting. So the modes that are going to become the Hawking quanta, when the infalling observer sees them, they are in their ground states. Okay, so I'm using the adiabatic principle, and this is there's a lot more to say about this. Let me figure out if I want to say it now or later. I'll say it later, because this is not the way that Hawking described the calculation. He didn't appeal to the adiabatic principle. This appeal to the adiabatic principle I'm making actually comes, I think it was Ted Jacobson in a paper that's in the note that it's cited in the notes, who first sort of organized the calculation in this way. But I'll explain to you sort of why later on why I'm doing it, why it's the way that things need to be done. So now the calculation. So I'm going to. I think I've erased part of my metrics. So I'm going to consider a to make calculations simple. I'm going to consider a massless scalar in 1 + 1 dimensions, and so I'm just going to drop the angular part. The metric is as before, but I'm going to drop the angular part. And so actually, let me write the relevant part of the metric up there. I've erased it, so I'll copy it. But I want to introduce two sets of coordinates. So u and v, again, are the global coordinates. U and v are the coordinates that would naturally be used by the infalling observer because they're smooth at the horizon. But I also want to write this this way, with the little u and little v, which you haven't seen before, are logarithmically related. And I guess to explain why I'm introducing them, let me introduce one more this coordinate relation. R star here is called the tortoise coordinate, and it's not the thing to focus on. The thing to focus on is that little u and little v are linear in the asymptotic time t. So the observer who falls through the horizon will naturally expand their fields in modes of given u and v frequency, capital U and capital V frequency. The observer who sits at infinity, which is flat space, will use the natural set of flat space modes, and so they will expand their fields in modes of given little u and little v frequency. And I see that I've painted myself into a corner here because that board doesn't raise. Boy, there's a lot of equations. Okay. So I'm gonna have to cover this up because I really want to write in the middle because there's kind of a lot of equations. But firewall papers and talks don't have enough equations, so this is why I'm doing this to you. But it's good to see it. For a massive scale in 1 + 1 dimensions, of course, the wave equation is really simple. It's partial u partial v of phi is 0, and because this relation is conformal, it just relates u to u and v to v. That's also the same in the global coordinates. And so the solution is functions of u plus functions of v in either coordinate set. And we're interested in modes which are outgoing. So they're functions of u. And so in particular, I think you really don't need that again. And so in particular, the observer who falls through the horizon, so this is just the right moving part of it. The observer who falls through the horizon is going to expand their modes, just the normal quantum field mode expansion. In terms of, again, global of the capital U frequency. While the observer who stays at infinity is going to expand those same modes in terms of the little u frequency. I'll call, so A is what the infalling observer uses, V is what the asymptotic observer uses. Okay. Now, these are the same expansion, just two different, the same field expanded in two different ways. And so by taking Fourier transforms, we can expand, in particular, we can expand B. Actually, which way do I want to go? we can expand B in terms of A and A dagger. So just by again Fourier transform, B omega is integral 0 to infinity d nu over 2 pi. And then there are some Fourier components that one can work out. They're in the notes. I won't write them on the board. They have gamma functions in them. They're not that bad. Okay, now finally we insert the physics. And the physics is that, again, the adiabatic principle says that the infalling observer sees these modes empty. So the physics, the adiabatic principle, so for any black hole that's been sitting around for a while and we haven't done anything to it, these modes are empty. And from that and from this relation, it follows that the B modes are not empty, and it's a short calculation. So I'll again let you refer to the notes for the numbers. But what you find is that the occupation number for one of these outgoing modes is thermal. With the expected temperature. Okay, so so the whole thing is, again, the way I've done it, and again the way Jacobson, I think, first presented it, using the adiabatic theorem to give you your initial condition, and then using the just the geometry to turn this into a calculation of the Hawking excitation number. Now, if any of you have read Hawking's original calculation, he did it differently. He integrated the field equation. So I've integrated the field equation basically from here to here, from infinity back to the near horizon region. He integrated it back further through the infalling body, and then there's an origin here, off the origin and back to initial infinity. That's always seemed kind of fishy because this blue shifting becomes so large that at the time these modes are passing through the black hole, their energies are far above the Planck scale. So this is not really a valid calculation, and it caused a certain amount of concern, and I think Jacobson sort of said it in the right way. So you don't need to push this calculation back through the infalling body. He got the right answer. It's hard to get the wrong answer because as long as your calculation incorporates the adiabatic principle, it will give the right answer, even if it has the wrong physics otherwise. And so he got the right answer, but the right physics is what I've described here. Yes, please. Yes. Well, I'm not sure what danger you're referring to, but I mean, we could simply do quantum fusion. I mean,
That's a statement of like principle.
well, actually, no, they don't, because in fact, in this calculation, the back reaction of those modes is not so large because we don't have it. They escape to it.
No, but I'm not even asking.
The next correction to this calculation. Actually, let me, before I answer the question, I don't know what your question. This is an important thing about gravity, which is that gravity is an irrelevant interaction. Like pion physics, which you heard about from Raphael, its coupling constant is 1 over a mass squared. It's 1 over the Planck mass squared. And so gravity becomes weak at low energy. And so if the first question, which is maybe not John's question, is what about the next correction here? And the statement is that the next correction is suppressed by something of order L Planck squared over the Schwarzschild radius squared. So in that sense, one would say it's a robust calculation. But what's your question?
My question is about the starting point. So, I mean,
Yeah.
So in my lecture, so maybe you should have argued when I said it in my talk that the only thing you know about quantum gravity is that the number of figures in freedom are not distributed over space.
Well, I'm just doing. I'm going to do. This is an important question. This is an important question. See, the question. Well, it's so. I should emphasize. I am, in the spirit of the statement I just made, I am treating quantum gravity as an effective field theory. I am using it. I'm treating it as an effective field theory, just as we treat low-energy pion physics as an effective field theory. Now, John knows that this is going to break down at some point, and he's already worried. But I don't want to jump ahead like that. I want to discover I want to get to the breakdown in a natural way.
But hasn't it already broken down in the sense that if you really did have
So I gave this somewhat hand-waving Bekenstein argument that says you can understand the entropy even with an effective field theory. Now this, and it's true. That is, if you try to put, so let's not go looking for problems quite yet. We'll run into them soon enough. But just I am using low energy effective field theory until it comes back and gives me trouble. And I'm not, yeah. Okay. Good. Where was it? Okay, so that actually is the main point. I wanted to reiterate. So I wanted to reiterate, by the way, this adiabatic theorem. I described to you, what it is and how it's used implicitly. Now, another way to think about the adiabatic. So there's an interesting commonality between black holes and the expanding universe, which is that there are modes that we're interested in, the Hawking radiation or the cosmological fluctuations. And by the way, this was already written on the board by Eva and by Leonardo because it's really the same calculation, but for cosmological perturbations. So there's a scale that we're interested in, which is the Hubble scale or the inverse Schwarzschild radius. This is energy. And then there's a UV scale. And the adiabatic theorem is a theorem in the region where we understand the physics. And there's always an implicit assumption that okay, there's some point beyond which we don't know what the physics is, but there's an implicit assumption that the adiabatic principle still applies. And so as the universe expands or the horizon persists and modes are basically redshifting from here down to here, the adiabatic principle says they kind of emerge empty. And as Andre Lindy likes to point out, if this were not true, then the expansion of the universe locally would be constantly frying us with trans-Planckian particles. So we kind of know that it's true. Although something Eva didn't talk about, but her recent work, we can't be totally sure. It seems hard to avoid, but we can't be totally sure that the adiabatic theorem applies to strings. Strings have funny properties when seen at high boosts and so on. I mean, this comes back maybe to John's question about how much do I trust my ability to boost by an infinite amount. And so maybe this, in fact, is a place where these arguments break down. But at this point, that's a long shot. I mean, it's something that one can try to study with calculations. So this is the physics that goes into it, into both the calculation of the cosmological fluctuations and the calculation of Hawking radiation. By the way, there are some poorly motivated, I think now largely sort of not followed up on, models of trans-Planckian physics in the CMB that don't respect the adiabatic principle. And again, I think they've largely been sort of ignored in the literature. Question?
So you say that adiabatic principle is start empty, they'll stay empty.
Well, first off, the Adiabatic principle says that in the regime where we can use sort of quantum field theory, if they start empty, they'll stay empty. And there's a further assumption, which is this regime that we don't fully understand. When they leave that regime, they leave that regime empty. Yes.
But that's separate from the Adiabatic.
That's separate. It's sort of an extension of it. Yeah. Be much more interesting if it were false. But yeah. Okay. So I didn't quite get to the information problem. I want to. I have three small just elaborations on Hawking radiation, and next time I'll start on the information problem. So the first is that these modes that we've used, the little u and little v modes, only cover region 1, whereas the big U and big V modes cover regions 1 and 2. So oops, forgot the squeegee. We need some additional modes. So here's the horizon again. So the modes I've been using are B sub omega, A sub nu, which covers the horizon smoothly. And so to really finish out the dictionary, we need an additional sort of inside Hawking mode. And it's true that B is like A plus A dagger, this with coefficients, of course, as written before. But turning it around, A is like B plus B dagger plus B tilde plus B tilde dagger. And the statement that A annihilates the vacuum annihilates the black hole state, implies that this is proportional to e to the minus. It's a squeezed state, a Bogoliubov transform state. Okay, so again, that's so whenever you have this kind of Bogoliubov relation between two sets of oscillators, oops, there should be a state on this side. It acts on the vacuum for the B and B tilde modes. Okay, so whenever there's this kind of Bogoliubov relation between modes, for the states it implies that the vacuum for one set of modes is a squeezed state for the other. In particular, this implies that B and B tilde are entangled, that the excitation level of B is equal to the excitation level of B tilde. So they're either both 0, both 1, both 2. So this is a squeezed state. It's an entangled state. By the way, actually, I didn't derive this, but you can sort of write this down by inspection. First of all, it's just a general fact that this kind of mixing leads to an exponential in the raising operators. Secondly, you can get the normalization here from the number operator, which was calculated before, that gave us the Hawking flux. The other thing is I've assumed it's diagonal in these two frequencies, which follows from translation invariance, but there's something funny here, because translation invariance is on the outside energy conservation. So the statement that this state sort of conserves energy, well, okay, so the creation operator for the outside mode adds an energy omega. It must be that the creation operator for the inside mode actually lowers the energy by omega. And that's true. So this mode has positive energy, and this mode has negative energy. And the point is that energy is associated with a killing vector. And on the outside, that killing vector is time-like, and it's the energy as seen by an asymptotic observer. But on the inside, that killing vector is space-like. And so what I'm calling the energy is something that would be identified by a local observer as momentum, which can be positive or negative. And in fact, for these modes, it's negative. In fact, if this were not true, if these modes did not have a negative energy, this wouldn't be translation invariant, and the whole thing wouldn't make sense. So you will hear people say that the way that black hole evaporation works is a positive energy particle falls into the a positive energy particle escapes to infinity, and a negative energy particle falls into the singularity. And it's true. It's true with the understanding that energy means this global conserved quantity. The second elaboration, actually, I only had one. Okay, sorry. Second and final elaboration, and then I'm actually done, is the massless scalar is really very, very simple because its modes are just right moving and left moving. And if you do this for massive scalars in 1 + 1, or you do this for any field in 3 + 1, then what happens is how to draw this? There's so the mode B that I've been talking about, as it leaves the vicinity of the black hole, has some amplitude to backscatter and some amplitude to escape. And similarly, there's an ingoing mode. I'll call this one C. This is B. Actually, well, so this I'll call this one B. And so the precise relation is B, the thing that actually gets out at infinity, has some amplitude to be, in fact, this mode. It's just, so it's the reflection amplitude. It's the reflection amplitude times the ingoing mode, and then the transmission amplitude times what it was before. So as before. And so in particular, the number is thermal times the transition amplitude squared. By the way, r squared plus t squared is 1. Okay, so this is normal. Of course, this is a gray body factor. It's why carbon is bad. It's right. Yeah. No, it's that. I mean, the reason we have a greenhouse effect is because carbon dioxide reflects at the it reflects in the infrared but not in the visible. So energy gets in but doesn't get out. It's the fact that T omega is a function of frequency. But anyway, sorry, that's getting ahead. For any so for a black body, it radiates the black body spectrum. For a gray body, a body which partly reflects, the thermal emission spectrum is correspondingly reduced. So this statement here is actually very ordinary statistical mechanics, but in the context of the black hole, where this comes about is because away from the horizon, kind of at a distance of order twice the Schwarzschild radius, you have this mixing of modes. It doesn't change anything essentially what I'm going to say, but it's something that to remember, because it does come up in various discussions. In particular, as you go to higher angular momenta, the transition factor gets very small. It's almost all reflected because of the centrifugal barrier. Anyway, so I only really got through Hawking radiation. So next time I will start with the information problem. Thank you. Okay, so there'll be a question period after the break, unless there are anything urgent. Thank you. Okay.
Okay, so it looks like this derivation assumes you can like factorize.
Ooh, in what sense?
Well, I mean, I would think that the big UV observer has a Hilbert space that extends across the horizon.
Okay, yeah.
But the little UV does not.
Right, okay, fair enough, yes. Fair enough.
My real question, though, is that so last week when Mark was talking,